So we want to look at another theorem. It's called the rational root theorem. Sometimes in other books it might be called the rational root or rational zeros test. What this is saying is that I can find a list of possible rational solutions or rational roots for a polynomial. Now, the reason we might want to use this is because with that factor theorem, the factor theorem said if I plug in a number or I do synthetic division, remember remainder theorem says I can do either, plug it in or I can use synthetic division. If I do that and the remainder is 0, then I know that I've got a factor and a solution. But the question is, where do we get those numbers from, right? Unless they tell us the number to plug in, how would I know what numbers to just start trying to see if the remainder is 0? So they came up with this rational root theorem or rational zeros test that says, well, we're going to come up with a list of numbers. We're going to try those numbers, see if the remainder is 0. If the remainder is 0, then we've got our solution. So now this rational root theorem goes along with those other two theorems to basically start off a list of numbers for us to then try to either synthetic division or evaluate and determine if the remainder is 0. Okay, so all we're doing here is we're making a list of numbers that are possible numbers. They're not all going to work, right? Remember when we did the leading coefficient test, it would tell us how many possible rational solutions that we might have. So say we're only supposed to have 4 rational zeros because say it was a 4th degree. I might come up with a list of 10 numbers. So clearly not all of those numbers are going to work on that list, right? But this will give us a starting point, okay? So the way that we're going to do this, we're going to use that leading coefficient again. Remember, the leading coefficient was what we used for that leading coefficient test in the beginning. So I'm going to use the number in front, that leading coefficient, and now I'm going to use the constant term, the term at the very end that doesn't have a variable. Okay, what I'm going to do is I'm going to take the factors of my constant. Remember, factors are numbers that multiply to be that value. So let's say I had the number 6. Factors of 6 would be 1 times 6 and 2 times 3. So those would all be the factors. Okay, so I'm going to take factors of the constant and I'm going to divide it by factors of that leading coefficient. I'm going to give a positive and a negative of every single number. Okay, so I'm going to set up this fraction and then I'm actually going to have to divide them to see what the actual numbers are on the list. So let's look at an example here. Let's say that we have the function f of x is equal to 4x to the 5th plus 7x cubed minus 2x squared plus 5x minus 6. Okay, and what we want to do is we want to come up with a list of possible solutions. So what I'm going to do is I'm going to take my constant and I'm going to take my leading coefficient. So I'm going to come up with factors of our constant. So factors of 6 is going to be 1, 6, 2, and 3. I'm going to give each of those a plus and a minus. Okay, because it could be a positive 1 and a negative 6, a negative 6 and a positive 2. It could be any of these numbers. Okay, then, and it doesn't matter the order in which we write them in. If you thought of 2 and 3 first, then that's fine. It doesn't matter. So now what I'm going to do is I'm going to divide that by the numbers that multiply to 4. So I'm going to get 1 and 4 and 2 times 2. Now, I don't need to rewrite it on the list twice. I'll just have it on there once. Okay, so this is going to be all of the numbers that I could use, but I need to actually make the list. So I'm actually going to divide these now. So I'm going to take the number 1 and I'm going to divide it by each number. So 1 divided by 1 is 1. 1 divided by 4 is 1/4. 1 divided by 2 is 1/2. And I'm done using that 1. Now I'm going to go to the next number. 6 divided by 1 is 6. 6 divided by 4, I'm going to go ahead and reduce it. That's going to be 3/2. 6 divided by 2, reduce that to be 3. Notice I'm putting a plus and minus on all of these. All right, now I'm going to go to 2. 2 divided by 1 is 2. 2 divided by 4 is 1/2. It is already on the list, so I'm not going to rewrite it. 2 divided by 2 is 1. It's already on the list. All right, so now let's get to our last number. 3 divided by 1, it's already on my list. 3 divided by 4, so I need to add that one. And then 3 divided by 2, which is already on my list. So now I've got the entire list of possible rational solutions. So for this polynomial, I would be trying 1, 2, 3, 4, 5, 6, 7, 8. I'd be trying 16 different numbers, right? Because I could try a positive one. I could try a negative one. I could try a positive 1/4. I could try a negative 1/4, right? And all the way through until I get to my positive and negative 3/4. All right, so remember what I mean by trying. I'm going to plug them in and either synthetic division or evaluate those numbers, and I'm looking for a remainder of 0. If I get that remainder to be 0, then I know that that was an actual solution to my polynomial, right? And you're like, well, do I have to use all the numbers? Well, think back to our leading coefficient test. Remember, our leading coefficient test said that all I need to do is look at the highest exponent to know that there's 5 possible rational solutions here. So we have 16 options here on my list. What if the first 5 work? Then I'm done. But you know what? What if negative 3/4 is a solution, and on my list it's the very last number? So I might have to try every single number. I might get lucky and find them in the first few. And then we'll look at later what happens when I've used all 12 and I don't find all 5. Because remember, we said it's 5 possible rational solutions. So this list is going to get me started to finding those solutions. I take factors of the constant divided by factors of the leading coefficient, and then I divide them out to get my complete list of possible rational solutions.